So hello everyone. Today I'm going to discuss about the Brayton cycle. So first is the history of the Brayton cycle. George Brayton designed the first continuous ignition combustion engine, or the Brayton's ready motor. The machine he invented introduced the process of continuous combustion, or the Brayton cycle, which became the basis for development of gas turbine. His machine made headlines in scientific journals of his time, but was superseded within a few years by Nicolaus Otto engine, a more efficient and quieter design. So here are the Brayton engine components: a gas compressor, a mixing chamber, and then expander. So what is a Brayton cycle? A thermodynamic cycle, also variously called the Joule or complete expansion diesel cycle, consisting of two constant pressure isobaric processes interspersed with two reversible adiabatic and isentropic processes. Now, the Brayton cycle is used for gas turbines only where both the compression and the expansion processes take place in the rotating machinery. So, Brayton cycle components. First, fresh air is drawn into the compressor, which pressure and temperature are raised. Then high pressure air recedes into the combustion chamber where the fuel is burned at constant pressure. The resulting high temperature gases then enter the turbine where they expand to the atmospheric pressure through a row of nozzle vanes. This expansion causes the turbine blade to spin, which then turns a shaft inside the magnetic coil. When the shaft is rotating inside the magnetic coil, electrical current is produced. The exhaust gases leaving the turbine in the open cycle are not recirculated. So, processes and how they occur. Isentropic process. So, it is the first part of the process. The ambient air is drawn into the compressor where it is pressurized. The isobaric process, the compressed air then runs through a combustion chamber where fuel is burned, heating that air. A constant pressure process since the chamber is open to flow in and out. Isentropic process next is the heated pressurized air then gives up its energy expanding through a turbine or a series of turbines. Some of the work extracted by the turbine is used to drive the compressor. Isobaric process, the last part of the process, which is the heat rejection in the atmosphere, where the heated air which went through the turbine goes into the atmosphere. So, Brayton cycle and its difference to the other cycles. The thermal efficiency for a given gas air is solely a function of the ratio of compression. This is also the case with the Otto cycle. For the diesel cycle with incomplete expansion, the thermal efficiency is lower. The Brayton cycle, with its high inherent thermal efficiency, requires the maximum volume of gas flow for a given power output. So the Otto and diesel cycles require much lower gas flow rates, but have disadvantage of higher peak pressures and temperatures. These conflicting elements led to many designs all attempting to achieve practical compromises with the development of fluid acceleration devices for the compression and expansion of gases. The Brayton cycle found mechanisms which could economically handle the large volumes of working fluid. This is perfected in the gas turbine power plant. So here is a Brayton cycle. First, fresh air is put into the compressor. Then, from the compressor, we have the compressed air is inserted with fuel, and then combustion happens. Then from the combustion, the expanding air rotates the turbine, which generates electricity, which is connected to a electromagnet, which or a dynamo, which creates electricity. So here is the PV and TS diagram for the Brayton cycle. So open and close Brayton cycles. So this is on the right side, we have the closed Brayton cycle, and in the left side we have the open Brayton cycle. So the open gas turbine cycle can be modeled as closed cycle by utilizing the air standard assumptions. Here, the compression and expansion process remain the same, but constant pressure heat rejection process to the ambient air replaces the combustion process. So here's the BV and TS diagram of the process. So from we can see here that the input happens at from point 2 to 3, where the combustion happens. So first is the isentropic compression from point 1 to point 2. The next is the constant pressure heat addition, the combustion. And then next is the isentropic expansion, the turbine. The expanded air passes through the turbine. And then the constant pressure heat rejection, where the heat is rejected through outside of the system. So here's a sample of a Brayton cycle, of a closed Brayton cycle. So heat added is the enthalpy of zero point 0.3 minus the enthalpy of zero point 0.2, which or the Cp of T3 of zero point 0.3, the difference between zero point 0.3 and zero point 0.2. So the heat ejected is the enthalpy of zero point 0.4 minus the enthalpy of zero point 0.1, or simply the Cp times the temperature difference of zero point 0.4 and zero point 0.1, which is the heat rejected. So the cycle efficiency for the Brayton is the net work, or the total work produced by the cycle divided by the heat added, or 1 minus the heat rejected divided by the heat added, or 1 minus the Cp delta T of the temperature difference between zero point 0.3 and zero point 0.2 divided by the Cp divided by Cp times the temperature difference of zero point 0.4 and zero point 0.1. So it just expands. So the efficiency of an ideal Brayton cycle is given by this formula. Pressure ratio. So 1 minus 1 over the pressure ratio raised to the constant, which is always almost always 1.4 minus 1 divided by 1.4. So that is the pressure ratio. So additional basic formulas for the compression. So we have P1 V1 raised to K is equals to P2 V2 raised to K. So this is the PV and T relationships for the isentropic process. So next is the compressor work, or the WC, which is equals to MCP times delta T, or the temperature difference from point 2 and point 1, where Cp is equals to 1.0 kilojoules per kilogram Kelvin or Celsius for air, and then pressure ratio is the ratio between the volume displaced and a P3 or of over P4. So another additional basic formulas for the heat added, we have the MCP delta T of zero point 0.3 and zero point 0.2. So the turbine expansion, or it is the isentropic process, we have P3 V3 raised to K is equals to P4 V4 raised to K. So it is the PV and T relationship for isentropic processes. Since the process from 3 to 4 is an isentropic process. So the work for the turbine is equals to MCP delta T from point 4 to point 3. Point 3 to point 4. The temperature difference. So next is the net turbine work, or the total work done by the system, which is the work of the turbine minus the work of the compressor. So for cycle efficiency, we have the work net over the heat added. So work net is the work of the turbine minus work of the compressor divided by the heat added. So back work ratio is the work of compressor divided by the work of the turbine. So for the ideal compressor work is the mass of actual times the Cp of actual times the delta T, or the temperature difference of point T2 and T1. So the actual compressor work, which is ideal compressor work divided by the compressor efficiency, which is equals to MCPA, which is equals to actual mass times the Cp, actual Cp times T2 minus T1, or the actual temperature, second temperature, it is actually just derived the formula, where the Cp, specific heat air ratio, say specific heat of air, is 1.0 kilojoules per kilogram. I'm sorry for saying ratio. And then there is another additional formulas for the ideal turbine work. So for the ideal turbine work, we have mass of the actual plus the mass, then the CPG, then delta T. So it's just the other formulas. So for the actual turbine work is the ideal turbine work times the turbine efficiency. So here are other formulas for the actual turbine work. So heat generated by the fuel is mass of air times the ratio of fuel times the heat added, and then yes, that's it. So for the actual network, work net is equals to the work of the turbine, actual work of the turbine minus the actual work of the net minus the work of auxiliary. So these are all the other efficiencies: overall thermal efficiency, generator output divided by the heat of fuel, so combustion efficiency. So that's it. Thank you for watching.